Good afternoon. This is the start of Chapter 8. Chapter 8 in our textbook is called Work and Energy. And it starts on page 251. And we're near the end of the first semester. This is Chapter 8. And this chapter, Work and Energy, is really a very, very important chapter. And in terms of, I would say, usefulness in concepts, the energy concept in physics is probably one of the most useful concepts that you will actually ever learn, and especially for you people who pursue more science and potentially even engineering in college maybe. The concept of work and energy will come up repeatedly over and over and over again in various different forms. But the fundamentals are actually right here in this chapter. The fundamental physics that we're going to learn in this chapter, if you learn these concepts well, you will actually be able to solve a wide variety of many types of problems. So this is an excellent chapter, and basically, what is energy? And if you look on page 251, there is right in the middle. There's a definition, and it says, "Energy is the ability to do work." Now, you may think, well, what is work? Well, physics has a very particular mathematical definition of what we mean by work. We use the term work in lots of different ways, almost like work. We go to work, we do work, mental activity can be work. But look from a physics point of view, look how work is defined on page 251. Work is a product of the displacement of an object and a component of the applied force that is parallel to the displacement. Okay, and if you flip over to page 252, there is a mathematical definition of work that goes like this. Work, and we will use this symbol W, equals force parallel times delta x. Okay. Now first let me say this, that energy, from a units point of view, work and energy, I'm going to change pens here. Work and energy have the exact same units. So we will use, from a units point of view, the units of energy and the units of work are exactly the same thing. Basically, the concept is this. Energy is work that's stored, or it's potential work. In other words, suppose you can think of it from the concept of a battery. You have a battery. All by itself, is anything useful? If the battery is not connected, is anything useful happening from the battery? No. But we know that the battery has the potential to do all kinds of electrical work. So once we hook up the wires to some kind of device, let's say a motor, say this is a motor, and the motor is on a shaft, and we lift up some mass. Here's a switch. This battery stores electrical energy. Okay, once we close the switch, it energizes the motor spins, and this mass is lifted up a certain distance, L. Okay, so work is done on this mass. This applies a force through the tension through the string. Okay, this mass is lifted and goes a certain distance L, and this is our delta x. The force, notice in this case that the force is in the same direction that the mass is traveling. Okay, so that's why we call it force parallel. It's force parallel in the direction that the velocity is going, direction that actually delta x is going also. Okay, and so from a units point of view, what units does force have? Force has units of newtons times meters. So work has units of Newton times meters, and we give that a special name. It's called a joule. So 1 Newton times meter is called 1 joule, named after the scientist and really engineer James Prescott Joule, and there's a little description of him on page 253. So he formulated a lot of these early energy concepts, and but let's explore this a little bit more. And what I'm going to show you now is actually it's actually not in this in the chapter here. But before I leave that, let me say, so work has units of joule, 1 joule, and energy has same thing, same units, joule, same units. Now in the metric, this is true. 1 joule of energy, 1 joule of, this is energy, or work, equals 1 Newton times meter. Okay. In English units, what would we have? We would have the force is pound, and length is feet. So it's foot-pound. We call it, or we abbreviate it, you may have even heard this, a foot-pound. And it's just called the foot-pound, and that would be the English unit of work. Okay? Okay, actually, let's explore this a little bit more, because actually force and displacement are actually vectors. And so if you would look in a higher level physics book, it would be explained like this, that the work is the force vector in a dot product with the displacement vector. Okay, and the dot product, I think we may have talked a little bit about this before, but if we have the force acting in this direction, but the displacement actually is in a slightly different direction, okay, and there's a certain angle between these, that numerically what this is that it's the numerical force times that displacement times the cosine of the angle in between. This is actually the definition of the dot product in 1D, one dimension. So now, and notice that if these two are aligned, if this angle goes to 0, if theta equals 0, then that means that the displacement is collinear with the force. And what's the cosine degree? What if theta equals 0, cosine of 0 degrees equals 1. So we just say it's the force times the displacement, and that's what's on the top of page 252, force times displacement. But they draw this force parallel, meaning that these two are actually parallel. But in general, it's really this. It's the force times displacement times the cosine of the angle in between. Okay. Flip over to page, or I'm going to flip over to page 254. 254 and 255. There we introduce the idea, or the book introduces the idea of kinetic energy and potential energy. Okay, and potential energy is, again, I'm looking at the bottom of page 254, the energy that is stored ready to do work. It's kind of like the energy that's in a battery. There's the potential to do work, but it hasn't been released yet. And then there's kinetic energy. Kinetic energy has to do with the motion. It's the energy of motion. And if you look on page 255, it gives the definition of potential energy and kinetic energy. Potential energy, we're going to breathe potential energy. We're going to abbreviate that PE equals mgh. Okay, and right below it, it gives the kinetic energy. Kinetic energy. The word kinetic means like in motion. I'm not sure the exact definition, but basically the idea behind kinetic is that something's in motion. So it's the energy of motion. Kinetic energy equals 1/2 mv squared. 1/2 mv squared. M is the mass, and v is the velocity. And we know what g is. G is acceleration of gravity, and h is a distance from some particular reference point. And we will explain this more. Now, the book, you will notice that the book does not really explain, in fact, it doesn't explain at all, where these formulas come from. But I want to take a little bit of time now. I want you to take these notes. I want to show you that actually you have, even though the author did not derive these, we're going to derive them right now. And you have pretty much all the concepts you need to, you have all the concepts under your belt pretty much to understand how these are derived, with a slight exception of I'm going to need to invoke a little bit of calculus. So this will be very good for those of you who are actually taking calculus, because I'm going to use a little bit of calculus here. But for those of you who are not taking calculus, or maybe working up toward calculus, this will give you something to look forward to. Okay, so let's take the first concept, potential energy, which is actually maybe it's an easier concept to understand. At least it's easy from a formula point of view. It's easier to derive this formula. And again, both of these formulas come right from the concept of work. What we have, and let's draw a diagram. Suppose we have a mass that's right here. This is our mass, m, and we want to raise it to a level. I'm going to dot this. We want to raise it up from here to here. So it's like this is a heavy brick, and we're going to lift it up. Okay, and this distance here is h. So we might say, let's say that x equals 0 here, and here x equals h. Okay, so now notice that in this case we're going to apply a force. The force is going to be in the up direction, so it's a force parallel to the direction that it's moving. Okay, we're going to lift it up, and the question is, how much energy does it take to go from here to here? How much energy does it take? Now, here's another important concept, and I think the book talks a little bit about that, but I'm going to talk about it also, and that's the idea of the conservation of energy. Well, actually, the book does talk about it a little bit later, the conservation of energy. And that's this. The idea is this, that the amount of work necessary, and I'm going to put the amount of work necessary to bring this mass up to here is equal to, I'll call that the work that you have to put into the work that you have to put in to the mass, if you will, to raise it up to here, is actually equal to the exact same work if you take the mass and just drop it and let it fall back down. That is, when, you know, if you take something and you drop it, it impacts the ground. Okay, well, that impact actually has the ability to do work. Okay, and so we're actually in this, if you think of this as a system, what I mean by system is this is a closed system, and we're going to put energy into the system. That is this area from here to here. We're going to put energy into the system and raise the energy of the system. In particular, this mass, raise the energy of the mass. It's at a higher potential energy. That's what we call higher potential energy. We have to put energy into the system. But once the mass is up here, there's a certain amount of energy because of its potential position up here. And if we release it, we can gain back that energy. Kind of like a battery. We put energy into a battery. It energizes the energy state. It raises the energy state of the battery. And then we can release that energy back out. Okay? Now, is a battery 100% efficient? No, there are losses in the system. But right now we're dealing with what we might call an ideal situation where there's no energy losses. So we're going to assume that the energy we put into the system is equal to the energy we can get out of the system. It's 100% efficient. Later on, we'll introduce the friction idea, and we'll remove that idea that we don't have to have 100% energy going in equals energy coming out. But so let's start from here. And this is most easy to see when we lift the system up. We're going to raise it up. So think of our work. Work equals force times displacement. Okay? Now, okay. Now, what is the weight? The weight of this mass, what is the weight? The weight is mg. Okay? The weight is mg. So, actually, you know what? We're going to first consider that the mass is up here. Apologize, I'm just reversing myself. We're first going to consider the mass is up here, and we'll calculate the amount of energy that comes out of the system as the mass falls from here down to here. Okay? I'm sorry, I had it backwards. Okay, the force acting down on this is gravity. So weight equals mg. We've seen that from the last chapter. And that weight is actually a force that acts downward, correct? Now, the work concept is that the work is force times displacement. Now, what I'm going to do is I'm going to look at a small change of force. Excuse me, a small amount of work is equal to the force times a small amount of displacement. Okay, imagine I now look just at a small displacement right here. The mass falls from here just right down to here, and it's a small displacement. Okay, the work that was done on that mass is equal to the force times that little displacement. That little displacement is mg. Excuse me, that little force is mg, so I'm going to substitute for the force, mg, and I'm going to multiply by the little bit of displacement. And when I do that, that equals the amount of work that I can actually, that I can gain out of the system, okay? Because it has fallen that distance. Okay, now what I'm going to do, the total work, so that is a small amount of work done by the mass from here to here. Now if I want the total amount of work from here all the way down to here, I want the total amount of work, I need to sum up, there's the summation sign, all of the little delta W's. So there's a whole bunch of these. There's number 1 here. Then I have another displacement here. There's another one here. So what I have a whole lot of these little delta W's because I have a whole lot of small delta X's, small displacements. And I'm going to sum them up. I have from I equals 1 to n, there's n of these things coming down here. So I sum them up, and I get the summation from I equals 1 to n of mg times delta x. Let's assume that the delta x is equal in every part. Okay, so I have a whole bunch of I'm going to sum up all of these little segments here. Okay, now what we're going to do now is we're going to let delta x get really small. Okay, so as delta x gets really small, this delta n gets to a large number. The formula is the same. I'm just making these delta x's really small. So I have a whole lot of them. The delta n is going, this n, I'm going to have n of these. And first I may have 10, but now I have 100. Maybe I'm going to let now n go up to 1,000. I'm going to have 1,000 of these. Okay? And from a calculus idea, introducing the calculus idea, is where we let this approach infinity, as large a number as we can conceive of. And what happens is, at that point, that's the calculus idea, the summation sign gets turned into what we call an integral sign, mg, and delta x here is replaced by dx. dx, the little d means differential, a differential x, or dx. So when we use, from the calculus concept, when we use the idea of dx, we mean an infinitesimally small x. It's a very, very, very small dx. In fact, we can make it as small as we possibly want to make it or need to make it. In fact, the dx approaches 0. It approaches 0 in the limit, but does it ever get exactly equal to 0? No, but we can make it, we can force it as small as we want to. Okay, and that's what we mean by dx. So, and here, from the calculus idea, we have limits. Just like we have I equal 1 here to n, we have limits here, and we place them here. We say, in this case, we're going to say x equals, well, we're going to start from here, h. Actually, I'm doing this backwards. So I'm going to start from h to x equals 0. we're going to start from x equal h to x equals 0. Okay? That's the reverse of if we were doing it upwards. Now, this is starting to get a little bit messy here. I apologize. I'm going to erase this right now just to get me more room. Okay, from the calculus idea, if m is a constant and g is a constant, so we can bring them outside the integral, as we say. And we have dx. Now, if you know calculus, you know that the integral of dx is simply x itself. So I'm going to say mgx evaluated between the limits of x equals h and x equal 0. Okay? Now, I'm running out of room here, so I'm going to put this up here. When we evaluate this integral here, we go mg, and then we put in the limits, x equals 0 minus x equal h. And so what do we have? We have the work is minus mgh. Okay? So notice what we have. We have derived this equation here, mgh. Where did the minus sign come from? The minus sign came from the idea that energy is released. When we have a mass up here and we drop the mass, energy is coming, we're gaining energy, if you will. We're gaining energy out of the system, out of the mass. And so whenever we have a work, whenever we have the numerical value of work is minus, that means energy is released. Okay, released to what is one question you might say. Well, released to do useful energy or released into kinetic energy. Potential energy, because of position, is released and is transferred to kinetic energy of motion. Notice, if you would just take a mass, a brick up here, and I'll use the pen as a brick, and we drop, this gains, but when it hits here, it has a certain velocity. So there's energy here, stored energy in this distance h, and this energy is transferred from potential energy into kinetic energy or energy of motion. So the potential energy, the level of potential energy actually goes down. Okay, that's why there's a minus sign. Okay, there's a reduction of potential energy, but now there's a gain of kinetic energy. Okay, so at this point we have derived, this is how we derive this equation, mgh. And it's by using these calculus concepts of going back to the original definition of force, that force is, the work concept of work is a force times a displacement. And we put in, what is the force acting on this mass? It's the force of gravity. We put that into this equation, substitute that for force. We sum all of these up. Okay, and then in the limit, in the differential limit of delta x going to dx, the summation sign changes to an integral sign, and we integrate this equation, and then we evaluate the limits of the integral, and out pops our answer, mgh. Okay. So at this point, I'm going to erase this, and now we're going to work on the concept of kinetic energy. Again, this is something even though there's no questions in the chapter dealing with how to derive this, you all have the mathematical ability to, I think, understand this. And so I think it's good for all of you to understand this. And I know all of you are not taking calculus, but I do want to introduce kind of calculus ideas and to give you practical kind of engineering applications and physics applications of how calculus is actually used. Okay, from the now we're going to look at now how to derive the equation for kinetic energy. Kinetic energy, which is 1/2 mv squared. Again, we're going to work with the idea of we're going to work with the idea of the strict definition of work. Work is defined as force, the parallel force times displacement. Okay. Now this is going to take let's see. There's two. Let me check my notes here. Okay. There are two concepts, if you will, without really have to be considered. The first one's a little bit easier. Second one's a little bit harder. And if the first concept here is that let's assume that the force is constant. Now, we didn't even mention that last time. When we're deriving the equations for